We present parameter adaptive approximate model predictive control, a method to adapt neural network controllers without retraining. Model predictive control, MPC, is a control strategy that requires powerful and expensive processors for online optimization. Approximate MPC, AMPC, resolves this by sampling large datasets and imitating the behavior of MPCs with neural networks that run in milliseconds on cheap hardware. Tuning the AMPC in real-world applications usually involves changing parameters in the optimization problem and retraining the neural network. Thus, every tuning iteration potentially takes days to recompute the dataset. As a consequence, the whole process can take weeks. We propose a method for tuning the AMPC without recomputing datasets and retraining neural networks. We achieve this using local sensitivities of nonlinear programs with respect to its parameters. Our AMPC architecture imitates both the optimal inputs of the MPC and its sensitivities. This allows us to use an approximate linear predictor online to adjust the output of the neural network to changes in model parameters. We showcase the effectiveness of our method by controlling the swing-up of real cart pole systems with a severely resource-constrained microcontroller that costs a few dollars. On this processor, our AMPC is evaluated in less than 2 milliseconds and generalizes across system instances with different parameters using the same neural networks. We initially sample a dataset from an MPC that considers parameters of a cart pole system given by the manufacturer's datasheet. A neural network that naively imitates this MPC does not achieve a swing-up on the real system that has different parameters from the datasheet. Instead of going back through the lengthy process of changing the MPC and recomputing dataset and neural network, with our method, we can now predict how the controls would change given the real parameters. Thus, our approach successfully performs the swing-up and stabilization. We disturb the controlled system by pushing against the pendulum. As can be seen, the controller keeps the pendulum in the upright position. It is robust against external disturbances. We also push the pendulum to the end of the rail. The controller keeps the system inside the constraints of the rail by first swinging the pendulum down, moving the cart towards the middle and then swinging it up again. It has successfully learned the constraints of the system. Further, our method allows us to use the same neural networks for a different cart pole system from a different manufacturer without retraining. We simply needed to retune the parameters. Similar to the controlled Quanser pendulum, it is also robust against external disturbances. Our implementation in combination with our parameter adaptation method represents a significant step towards practical applications of AMPC in systems with varying parameters.